when we were solving difference equations with two of the same roots, we ran into a bit of a problem. So in this example, the root is equal to 2 of the characteristic equation. So that means that the nth term, our solution, is a times 2 to the power of n, which is the first root, plus b times 2 to the power of n for the second root. But the problem is, and then normally we'd solve for a and b using t0 and t1. The problem is this doesn't encapsulate all that information, because if we factor out a 2 to the power of n, we get a plus b. So even though it looks like we have two unknowns here, it's really just one unknown, because this is just some number. So the solution that I offered when I did the video is I said we just multiply the second one by n, so now these are kind of separate and they can't be combined together. Maybe you don't find that because now we have bn here. This isn't just some constant that we can combine into one constant, now it's something that depends on n. So the question is, why would we even think to try that? And the way that we're going to think about it is kind of like the way that you'd use the way that you prove things in calculus do with derivatives. We're going to look at something very similar. So instead of saying that the two roots are exactly equal, so in general we'd have a r1 to the power of n plus b r2 to the power of n. And basically the problem that we're running into is that r2 is equal to r1. So instead of saying that r2 is exactly equal to r1, let's do a little trick where we say it's equal to r1 plus epsilon, where epsilon is some positive number. It doesn't actually really matter if it's positive or negative, but we're just going to say it's positive. And epsilon is very small. Okay, so basically we're going to look at what happens as epsilon gets really close to 0, which means that r2 gets really close to being equal to r1. Well, let's see what happens. Well, then our equation for Tn would be a times r1 to the power of n plus b, and here we're going to have r1 plus epsilon instead of r2 to the power of n. And let's start multiplying this out. So r1 to the power of n plus b. So the first term is r1 to the power of n. And this is exactly the solution as up here, okay? So this is what we would guess our solution is when this is r1. We would guess that it's a r1 to the power of n plus b r1 to the power of n because it's the same roots, and this is what we get, okay? But that's kind of like a first order approximation. We kind of want to get one more level of detail by expanding out and seeing what happens, okay? So for the next term, we'd get n choose 1, r1 to the power of n minus 1, multiplied by epsilon. The next term would be n choose 2, r1 to the n minus 2, epsilon squared, and then we keep adding stuff. And basically, we're going to use a similar idea to in calculus here, that when you're trying to prove things to do with derivatives in calculus, what you end up doing a lot of the time is you say anything with like a dx squared is so small that it just doesn't matter and we just leave it. So for example, you can prove that the derivative of x squared is 2x by drawing a square and seeing how its area changes, and you just ignore anything with epsilon squared, like a very small number squared or any higher power, you completely ignore. So the idea is, as we get really close to 0, this part doesn't matter as much. This doesn't matter. We could think about trying it, but we're not going to try it for now. But we are going to try using this. And the reason we're going to try using this is because when we approximated it with just r1 to the power of n, it didn't really work out. So maybe let's just think about trying this part, because maybe that'll help us out. And then if that didn't work, then we might try using more terms. But it turns out that we don't need to use all those terms. So then we get Tn will be equal to a times r1 to the power of n plus b times r1 to the power of n, multiplying out the bracket. So this is exactly what we thought we'd have, right? This is what our initial guess would be, as up here. But again, we have the problem with the two unknowns combining. But now we have another term. We're going to have b. N choose 1 is actually just always equal to n. And we have r1 to the power of n minus 1 multiplied by epsilon. Let's simplify this a little bit. So this first part, remember, it kind of all combines into 1, because we just get r1 to the power of n times a plus b, and this is just some number, right? It's just some number times r1. So that's not super useful to us, because we need two unknowns for our initial conditions. But then what we have is we have bn epsilon. I'm going to say r1 to the power of n divided by r1, just so that you can see how it lines up here. And now what we notice is b times epsilon divided by r1, that's just some constant. That's just some unknown number. In the same way that a plus b is just some number, this stuff is also just some number. So I'm just going to call this stuff d, and I'm going to call this part c. So that means that Tn will be equal to r1 to the power of n times some number, c. Up here, I wrote it as a r1 to the power of n, so I'll actually do it the same. So I'll say c r1 to the power of n, right? And then we're going to have plus. And then here, okay, so we're going to have n r1 to the power of n. And then the rest of the stuff, the b epsilon and this r1 on the bottom, that's just going to be some number constant, which we call d. So this might be another solution we decide to try as another approximation, and it turns out when you sub this into the original difference equation, it does end up working. And if it didn't work, then what you could do is you could just try some other terms. There is some other stuff you can do in terms of derivatives. So like one thing you might notice is that the derivative of this would be n times r1 plus epsilon to the power of n minus 1. And it's kind of the same argument where we're now multiplying by an n, and we have an n minus 1 in the power of the r1. I couldn't really figure out a good way to explain this when I was researching. I thought this kind of way, but maybe you can mess around with that for yourself. So the last thing I think I'll do for this video is I'll prove that it works. So here, this example up here was a problem. Well, it was an equation we had when the root, was equal to 2. So here r1 is equal to 2. Okay, so let's see if this solution works. So Tn is equal to c times 2 to the power of n plus dn times 2 to the power of n. I'd encourage you to try it yourself, but I'm going to do it here now. So t sub n plus 1 then would be 2c times 2 to the power of n plus, and then this is going to be tricky. Okay, we'll have 2d 2 to the power of n times n plus 1. And we'll just simplify all that later. So 2t of n plus 2 would be 4c times 2 to the power of n. That's just because it's going to be the power of n plus 2, and then I'm just separating the plus 2 part to be that's 4. Then we'll have 4d times 2 to the power of n times n plus 2. And now let's sub it into the original equation and see if it is indeed a solution. So we have t sub n plus 2, that's going to be this stuff. Then we have minus 4 times t sub n plus 1, which is this stuff. And then we have plus 4 Tn. So then we have plus 4, and then Tn is this part. We want to see is what that, well, we're guessing it's going to be equal to 0, but let's just do a little check. Okay, so we're going to have to multiply out some terms. So here we have 4c times 2 to the n. Here we have minus 8c times 2 to the n. And then we have plus 4c times 2 to the n. So they're all common terms, and they cancel. Cool. So then we have, this is going to be, okay, we'll look at 4d. So this is going to be, oh, this is meant to be 2 to the power of n, isn't it? 4d times 2 to the power of n. Yep, I just copied that down wrong. This part here, at 2 to the power of n. Okay, so this term, we're going to have 4d 2 to the power of n times n. And then here we have 2d 2 to the power of n. So we have 4 plus 2 there, I believe. Or sorry, it's going to be, okay, I'll keep track. I'll write in green above. So we have 4 of these terms in green. Here we have minus 8 of those terms. And then here we have another plus 4 of those terms from that 4 out the front, from the 4 out the front down here. So yeah, basically we end up getting 0 again. Cool. And then finally, I'll use pink. We have the constant terms. Well, the terms not involving n, I suppose. We have this 4d times 2 to the n times this 2. That'll give us 8 of those terms. Then you have this 2d 2 to the n times this 1. But then it's multiplied by the minus 4 as well, so we get minus 8. So the minus 4 out front, the 2, the 2, and the 1, that gives us minus 8. And then down here, we don't have any because we're only multiplying by n, so we don't end up multiplying by a constant. 8 minus 8, they cancel out, so cool, it's always equal to 0. So yeah, that's the solution.